some questions, and we're going to introduce you to an idea that's called a probability tree. This is question 14, and I'm going to do question 14 two different ways. I'm going to do it just the kind of formula number crunching way, and then I'm going to show you that same question, but we're going to use this thing called a probability tree. Now, the probability tree is great as long as there's not too many things happening. As long as you don't do the same thing, 10 times. If you do it 2, 3, or 4 times, probability tree will work fine, right? Just a different way, getting your answer. If it's 7 or 8 times, you're going to have to do it just with number crunching. So there's a bit more to this story than is written down. So there's this girl, high school, and they have a homecoming day parade once a year in October. And she's there for 4 years. And historically, the chances that it rains on the parade day is 0.26. And it's independent each year. So next year, even if it rained last year or didn't, it's still 0.26. And the third year, it's still 0.26. And in the last year, it's still 0.26. And we're now going to be asked a number of questions about the weather during the homecoming day. Now, this one says, what's the probability that it doesn't rain on the first year? Well, if you know the probability it rains is 0.26, isn't not raining the complement? And are we okay with 0.74 as being the answer that goes there? That makes sense? It rains 0.26. I would, instead of calling it not rain, I'd call it dry, but it's just semantics, right? 0.26, or it ain't that, so it's 0.74. Now, it gets a little bit messier when you do not rain for all 4 days, right? Each of the 4 years, right? It doesn't rain. Because I'm going to call it NR for short. It's going to be not rain, not rain, not rain, and not rain. Now, because these are independent, can't we use what's called the multiplication rule and just multiply each of these probabilities together? So what's the chances that it doesn't rain any of the 4 times in the year she does it? One each year. 1, 2, 3, 4 not raining. Multiply each separately. And what do you have? You have a 0.74 times a 0.74 times a 0.74 times a 0.74. And that's what calculators are for, right? I could do that as 4 multiplications. Isn't there a shorter way to do the same thing multiplied by itself 4 times?
Power of 4.
So the power is that funny little underneath the clear button. It's a caret button, 4. And you're going to get some ridiculous answer, but they want the answer to 3 decimal places. And so to 3 decimal places, this guy ends up being, that 9 gets rounded up, that 9 gets rounded up. Technically speaking, 0.300. Are we cool with that? Now, I've actually calculated the wrong one. I have calculated the chances that it rains every one of those 4 days, which is fine. I misread the question. So let me do the probability that it doesn't rain, because I've actually done raining all 4 days.
I've done it with the calculator. Am I supposed to be coming up with about a 0.299?
Yeah, that's what I got. So let's do the not rain. Not rain. Now I've got my brain together. Not rain and not rain. It's just going to be 0. Wait a minute.
I think you did it right the first time.
I did it right the first time, so I don't care. I did it right. How about that? I did the question right, and then I talked myself out of doing it right. That's a bit different for me. So that's not raining, right? In question C, we're going to find out what's the probability that it rains at least once in those 4 days. And the key sentence here, the key part of it, is the at least once. Now, you recognize this guy and this guy. These are complementary events. So if I know this one, don't I know this one? So it doesn't rain for 4 days, or it rains at least once in 4 days. Isn't that going to be the 0.7 guy? Do another one of these before I do the probability tree then. Too many rains and not rains. Let's say the probability that you get the number 6 when you roll a dice is 1/6. Would you agree? What's the probability that you get 3 6s in a row? Well, won't that be 1/6 times 1/6 times 1/6, because rolling dice are independent events. Are we good? And on my calculator then, I can make that 1/6 cubed. So I go to my calculator and I'll do a little bracket, 1/6 to the power of 3, and I'm going to round this answer off to 4 decimal places, and it's 0.0046. So if the question was, what's the probability that they were all 6s, right? Because that's maybe just another way of saying it, right? The answer is that guy. What's the probability at least one of them is not a 6? All of them 6s, at least one of them not a 6. These are complementary events. The minute you see the word at least once, think of it as a complementary event or something. And in this case then, the answer would simply be 0.9954. So if you roll 3 dice, isn't there a really, really good chance at least one of them's not going to be a 6? If you roll 3 dice, the chances that all of them are 6s isn't that tiny? That kind of makes sense, doesn't it? Right, so if I go back to this one, not raining 3 times in a row, or 4 times in a row, I should say, is about 0.3. It rains at least once is the opposite to that, the complement, 0.7. So you should always be able to get an at least once by just taking this one, where all of them are the thing. Do you want to see another one of these? All 3 and at least 1? Are we cool with that process now? One more? Okay. Let's do weather again. And I'm not going to do this rain, not rain, because that just hurts my brain. So the probability that it's cold in any given day is 0.7. And the probability that it's hot is therefore going to be 0.3. Because in my weather system, it's either hot or it's cold. There's nothing else allowed, right? It's a two-stage weather system, right? It's dry and it's not dry, right? It's snowing and it's not. I'm going to call them hot and cold. That makes my brain think a little bit clearer. So we would like to know, what's the probability that you have an entire week, 2, 3, 4, 5, 7 days in a row where it's cold, right? And we'll assume that they are independent, right? Whatever happens today has no effect on tomorrow's weather, whether it's realistic or not, doesn't matter. So won't that be 0.7 times a whole load of 0.7s? And the short way of writing that would be 0.7 to the power of 7. You think that number is going to be big or quite tiny? What's your gut feeling before I hit the buttons? 0.7 to the power of 7. Any gut feelings? Here goes. 0.082, or about 8.2%. In my brain, percentages are easier to understand. So there's about an 8% chance, if you lived in this place, that you could get a week of nothing but cold weather. Now, what's the probability that at least one isn't cold? Or I could phrase it like this: at least one day is hot. Would you agree that's the same thing, just phrased differently, right? So, well, isn't it the complement of this guy? All of them cold, or at least one is not cold? That's another way of saying at least one of them is hot. And the answer is 1. Take away this guy, and you will get 0.918, or 91.8% chance. So a pretty good chance that you're going to get at least one hot day, aren't you? 90% of the time, in any given week, aren't you going to at least have one hot day? Whatever hot means. So the trick here is the multiplication rule allows you to find cold, 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 cold all the way through. You just multiply the same guy by 2, 3, 5, 7 times. And then when you want to do the at least one situation, you just take the complement of this event, and that will get you the at least one of the opposite event. So let me show you a probability tree, and I'm going to use this one here. The probability that it rains is 0.26. And instead of saying not rain, can I just call that dry to make my brain work a little bit cleaner, right? So what you do in a probability tree, and it gets its name basically because its shape is, you start here and you draw 2 little branches, and one of them is rain and the other is dry. And on the rain, you put 0.26, and on the dry, you put its probability, which is 0.74. And that basically is, on the first day, the chances that it rains is 0.26, and the chances it's dry is 0.74. You then have the second day, rain, dry, rain, dry. And it's still 0.26 raining, and it's still 0.74 for being dry, 26 for raining, 74. Can you see why this picture is really only good when there's only a few number of days? Can you see it's going to get bigger and bigger? So if let's change this story just to 3 days, because then I can do this quicker. So let's suppose she's only there for 3 years. You can see how bad my drawing has got because I didn't kind of plan as well as I should. Should have brought it down a bit, but never mind. I've got 26, 74, 26, 74, 26, 74, 26, 74. Now I can use this diagram to find the probability of lots of other things, but let's just do the rain 3 days in a row. You want to know the probability it rains 3 days in a row? Well, 3 days in a row goes this way. It rains, then it rains, then it rains. So to get that probability, You just multiply the pathway together. And this is a slightly different number because it's a different number of days. I get, as an answer, 0.018 because I'm rounding off. What about getting 3 dry days? Well, if I wanted to get 3 dry days, don't you follow this pathway? And that would get me 0.74, another 0.74, and then a last one, also 0.74. And 3 dry days ends up being 0.74 out of 3, ends up being 0.405. Maybe you would like to know what's the probability that you get 2 dry days and 1 rainy day, right? 2 dry days and 1 rainy day. You couldn't do that question using this technique. It wouldn't really be feasible, but you can do it on a tree diagram, right? 2 dry days and a rainy day. So let's see which one of them that would be. Dry day, rainy day. Would you agree that's 2 dry days and a rainy day? Is there any other combination in here that would get you 2 dry days and a rainy? Right, can you see where it is? Maybe a bit hard to tell.
Absolutely.
Here? Rainy day, dry day, dry day. Wouldn't that be, wrong one? There. Right, rainy day, dry day, dry day. So this guy here and this guy here, right, this destination represents, as far as I can tell, well, what about this one? Dry day, rainy day, dry day. Would that one also count?
Mm-hmm.
Right, I think I've got them all now. Now, what do you do with these 3 answers? You find their probabilities, and then you add them all up, and that's the probability of getting 2 dry and 1 rainy. We're not. Say again, Rob?
Oh, I'm sorry. I forgot to hit my mute button.
Okay, I'll just mute you, and you can hit it when you want to say something. That'll make it easier for you, right? So if I wanted to do this one, for instance, it would be rain, dry, dry. So rain would be 0.26 and 2 dry days. And then whatever that came to would be the answer. And that would be about 0.142. Can you trust me that this one also ends up being 0.142, and this one here also ends up being 0.1412? So if you add them together, wouldn't that be the probability of getting 2 dry and 1 rainy? And you can use these tree diagrams to do lots of other much more complicated probabilities than you can do with this.
Okay, I got a question.
Yes.
Being that probability shows up more than once in a tree, do we have to divide that final number?
No, you don't need to divide anything. You're always multiplying in these questions. What you might have to do is add up some destinations, like in this second one that we did here, but no, you won't divide anything. There's no need to.
All righty.
Well, let's have another shot at one of those stories that look more like this. Oh, almost forgot. There is a term that you're going to see occasionally. It's called with replacement and without replacement. That's going to happen at definitely it's going to be happening at the end of chapter 7 when we do the 3rd one. But when you are picking more than one person, or one thing, If you do it with replacement, it goes back into the pile and you could pick it again. And if you do it without replacement, you can't use the same one twice. So without replacement, it's easy to say. You can't use the same item twice. And with replacement, you can use it twice. I'll give you an example. Suppose you had a bag, and in this bag, there were 3 blue beads, and there were 2 red beads. And you're going to pick 2 beads out of the bag, right? You're going to go like that and pick one out. Now, if you pick it out and put it on the table, and then you go back into the bag and pick out another one, that would be without replacement. Would you agree? If you use that red one, it's gone. With replacement, same bag, same beads, you pick one out, you look at it and say, oh, it's red. You write down it was red, but you put it back in the bag, give it a shake, and then you stick your hand in again. In that situation, can you see that the probabilities change, right? They're different in each situation. So let's do a probability tree and show you what that might look like. I'm going to take 2 things out of this bag, 2 beads. And they can either be red or they can be blue. Okay. And we're going to do this first one. We're going to do it without replacement. Okay. What's the probability that you stick your hand in this bag and you pull out a red bead?
2 out of 5.
Agreed. What's the probability you stick your hand in this bag and we're starting from scratch. You stick your hand in this bag and you get a blue bead.
Three out of 5.
Great. Now, since we are doing without replacement, that is going to make a difference when you come to take the second bead out the bag. It could be red. It might be blue. But the probabilities have changed. So the first bead was red. That's what that's telling us. That's happened. We know it's gone. Isn't the bag now going to look different? Isn't the bag going to only have 4 beads in it? Right? And how many of those beads are red ones?
1 out of 4.
184. Now, on the same story, the first bead was red, right? So that one's been used up. Would you agree there's still 4, but now there's 384? Do you see these 2 things are still complements of each other? They're just complements with different fractions, right? They add up to 1, right? If the first one was a blue, doesn't that become 284? Because there's 2 reds out of 4. And, oh, if the first one was a blue, haven't they kind of averaged out? I guess I could call them a half. Now I've got this tree diagram. Let's look at the probability that you get 2 reds, right? That both are red. It's going to be 2/5 times 1/4, which ends up being a 1/10. What's the chances that they're both blue then? Right. Oh, both red would be that pathway, right? Both of them being blue would be this single pathway. So it would be 3/5 times 2, and that's going to go to, that's going to be 3/10. Is it a surprise that in this bag, you're much more likely to get 2 blues out of a bag than getting 2 reds out of a bag? It seems reasonable, doesn't it? But the disparity between the 2, doesn't that look bigger than you would have thought? Isn't this 3 times more likely than that? And when you look at this, you say, okay, it's going to be a little bit more likely that you get blues, but isn't it a lot more likely? 3 times more likely. Now, if I did that same story, but we do it this time with replacement. First bead comes out the back. Well, it's 2/5, and the blue is still 3/5, right? Because there's really nothing happening there. It's the first bead. Now, if we go to the second one, now things do become different. Okay. Now, in this story with replacement, the first bead was red, right? You looked at it, you wrote down it was red, but it goes back in the back. Isn't the chance that the next one's going to be a red still 2/5? That makes sense? And isn't this 2/5? And isn't this 3/5? And isn't this 3/5? So let's find out what these two probabilities look like in this new situation. The chances that both of them are red is 2/5 times 2/5, which is 4 out of 25. And the chances that they're both blue is 3/5 times 3/5, which is 9 out of 25. It's still easier, isn't it, to get two blue than it is to get 2 red? But look at the difference. Do you see it's just a little bit more than twice as likely? So with replacement or without replacement, it does have a significant effect on probabilities, right? Whether you keep the thing and use it again, or whether once you've used it, it gets thrown away. Okay, we've really almost finished these ones. So let's do a woman having a child. This is 16. According to this, the probability that you have a boy child is 0.535, and they are independent of each other. So when they're independent, it's a bit like without replacement, right? With replacement, I should say. What's the probability that she has one of each children? Right, well, first I'm going to have to figure out what the girl is. And would you agree the girl is the complement of the boy? So it's the other 0.465. I'm going to do this with a tree diagram. You could have a boy, or you could have a girl. You could have a boy, or you could have a girl. And we are going to be using this tree diagram to find out what's the probability that she has one of each sex. Which I guess is another way of saying she has one boy and one girl, right? Now the boys are 0.535 and they are independent, so they're always going to be 0.535. And the girls, they're 0.465. It looks like that. Now, there are 4 destinations. We're looking for one boy and one girl. Which of these destinations, right, which of these 4 guys at the end are going to be a boy and a girl happening?
The 2 in the middle.
Did you agree this one and this one? Agreed?
Yes.
Now, this one would be a boy as your first child, then you got a girl. And wouldn't that happen by multiplying the 3 together? You always multiply the 3 values together. And this one, the first one happens to be the girl. And then the second one happens to be a boy. Aren't they actually the same 2 numbers, but in different orders? Which is not really a surprise. So on my calculator, I'll just do the top one. 0.535 times 0.465 And I'll round the answer off to 3 decimal places, and I get 0.249. And I'm pretty sure that one's 0.249. So the chances that you get one of each is 0.249 plus another 0.249. So that's going to be 8, carry 1, that's going to be 9. About 0.598. So there's a 59.8% chance that you get one of each. Do you see how that tree diagram method allowed you to figure out how to do that? Because if you didn't have that tree, aren't you tempted to just say, well, it's a boy and then a girl, so I'll just multiply these two and get that number and think that was it? Because you don't always notice that the order's important, isn't it? A boy first and then a girl second is not the same thing as the girl being first and the boy being second. And especially if it went to 3 children, you know, if we did this tree one more level, wouldn't it be much more difficult to say 2 boys and a girl? You know, what's the chances of that happening? What you do is you create your tree and then you look at the destinations, which is what I call these guys. And then to find them, you multiply the roads that you took to get there. So that times that, that times that.
Professor,
Yes.
apologies. I believe it's 49, not 59.
Yeah.
24/9 plus 24/9 is 49/8.
Did you all catch that deliberate mistake that I put there just to see if you were paying attention? Does anybody here believe what I just said? No, you shouldn't. Thankfully, it means you know what was happening. But, you know, when I do things, we always bear in mind it's the process I'm talking about, and you can make sure that the details are right there. Let's finish with 17, and then we can move on to the next section then. 17 has got another one of those at least one things going on. So in question 17, the probability that you win in a casino game is 0.4. So I guess that means the probability that you lose then is 0.6. Great. Rather than say not win, I'm calling it lose. We want to know if someone plays the game 4 times, what's the probability of winning at least once? So probability that you win at least once in 4 tries. Now I could, but I'm not going to, build a tree diagram. But wouldn't my tree diagram have to have 4 levels to it? Can you imagine how horrendously big that would be and how long it would take? I mean, it could be done, but I don't want to do it because of time. So there must be another way of doing that. Well, the probability that you win at least once in 4 times, maybe I could find its complement. Because one take away the probability, and I'll just call it right now, the complement of this thing, wouldn't that also be the same answer? So winning at least once in 4 tries, what's the exact opposite of winning at least once in 4 tries?
Losing all 4 tries.
Are you all good with that? The opposite, the complement is just another word for opposite, of winning at least once. Isn't that losing all of them? Now, don't we know how to do a 4 loser? Don't we just multiply this guy 0.6 times 6 times 0.6 times 0.6? So what we're going to do is 0.6, that fella. And in a calculator, 1 take away 0.6 to the power of 4, and I got 0.8704, which is about 87.04%. And maybe that's how casinos work. You know that you lose in casinos, but at least some of the time, 87% of the time, if you played 4 games, aren't you likely, you know, win one it? You're not going to get any money out of that, because won't you have lost a lot more money than you'd win because you had to play 4 games and you only got it 87% of the time. And we are finished with A. So we're now going to do probability. Part B. And I'm going to zoom right over to the homework once I've set it up. Okay, got a joke for you while I'm getting this all set up. Does anybody know which knight of the Round Table built the Round Table? No one know? It was Circumference.
Ooh,
Oh.
boo.
Boo! I'm getting a boo. That's a pretty tough crowd. Okay. One of my calc students told me that, so I thought I'd tell you. Now I'm beginning to regret telling you, but never mind. So let's see what is in store in Part B. It's been a while since we did the intro, but we actually covered this. In each of the following, is each of the following a legitimate probability? So could you get a probability with this number? Okay. 0.55. Not meant to be a trick question, meant to be a pretty straightforward one. Could you get 0.55? Yes. Could you get 0.00?
Yes.
Could you get 1.00? Could you get 1.01? Because it's bigger than, right?
No.
But in this case, it's a yes. See how easy these guys are? What about 1.15?
No, if it's over 1, it can't be a probability.
Right, and it's because it's bigger than 1, right? So when it's a no, you've got some choices for why it's a no. Would you agree that negative 0.35 is also a no? Which of the 3 reasons is your justification? Which of these 3 to make it a bit bigger? Can
Probability cannot be negative.
I? Okay. So nice easy start. It's, you know, what you see is what you get. I'm going to shrink this back again. Now, suppose you live in a city with 126,000 people and you randomly select 850 of them. What is the probability that your household is going to get chosen? Again, don't overthink it. Is it the answer going to be 1 out of, well, not 1 out of, 850 out of 126,000? Agreed? That's it. I mean, you've came from questions that you had a lot of work in diagrams and stuff, so your brain is maybe still on, you know, difficult things, and it isn't necessarily so. A car dealer has noticed that 4 out of 10 new car buyers returns the car for warranty work within the first month. I don't like that car. I don't want to buy a car if 40% of the people who buy one from him bring it back because the brakes are squeaking or the window's not opening or something, right? A warranty work. But it is what it is. Write a sentence expressing this fact as a proportion. So in this case, it looks like the proportion is going to be a fraction. So which one of those, 1, 2, 3, or 4? Which of those guys represents that story?
The 2 out of 5 will return their cars for warranty work.
So we're talking about that one, right? The third one? Agreed. Now, if you want to express that same piece of information as a percentage, don't you just figure out what 2/5 as a percentage, and would we be agreeing that it's 40%? But make sure you read it, because I was about to put it on the wrong dot. And then write this as a probability. What? Write a sentence expressing it as a probability? I think that's really just the same as that sentence, isn't it? They just stuck the word probability in front of it, not really nothing else. So it's going to be 2/5. So it'll be that one. Okay, let me leave this for a minute and talk a little bit about what they're using in these next couple of questions. And we're going to look at what's called relative frequency and how that interacts with probability. Suppose you collect information and you've got a guy here called frequency. That's just how many people. And let's see. And you ask them something really mundane because I can't think of anything good. So you ask them what's their favorite beverage, and it's Coke. You can only pick one. It's Pepsi. It's, I've forgotten what it's called, Dr. something.
Pepper.
Pepper.
Okay, so how about DRP, Dr. Pepper, or none, because I don't like, any of those kind of products, right? And you're interested in just relative things, and you get 120 like Coke, 100 like Pepsi, 50 like that, and 30 like that. And it's not uncommon that you add them all up and you get a total. And then there's another column I'm going to create, and it's called the relative frequency. Does anybody know how you calculate the relative frequency from this table?
I'm going to take a guess and say that you divide the number by the total.
And you guessed correctly. So the relative frequency would be these guys. And when you do relative frequencies, as I've got here, you should typically, you turn them into decimals. So 0.4, 0.167 roughly, 0.333, and 0.1, right? So relative frequencies are almost always written as the decimal version of the frequency divided by the total. In other words, 0.4 of the data were Coke. And you can see from these, although you could tell from this, that Coke's most popular. Now, as a check, provided there isn't any little minor rounding off errors, what will the total of a relative frequency always add up to if you do it correctly?
1.
1. So you can always use that as a quick check. Now, the reason why I kind of qualified it is, do you know that I had to round this guy off to 3 and this guy off to 3? So couldn't you end up with 0.999 sometimes and 1.02 sometimes? That's normally okay. That just means the way the thing's rounded off, hasn't always worked. Because can't you end up rounding everybody up and nobody gets rounded down, just the way the numbers come out? And that's fine when that happens. So you can use relative frequency, i.e. these numbers, in connection with probability. And it might go something like this. What's the probability that I pick somebody at random from this survey and they like Coke? Well, the answer would be the relative frequency. There is a 0.4 chance. Would you agree? 120 people out of 300. So the probability of picking one person from your sample is the same as the relative frequency of that subgroup. So the probability I pick somebody who likes Dr. Pepper is 0.167, right? But you can even phrase the questions kind of back to front. What's the probability that you get somebody who didn't like Coke? What would be that probability? You pick somebody from here and they don't like Coke.
60%.
0.6.
Yeah. Isn't that the complement? You could even say, what's the probability you pick somebody who likes Coke or Pepsi? Now, in that situation, wouldn't you add the two together? So can you get lots of probabilities from a sample and using its relative frequencies? Isn't it just a matter of, adding some together, or just using one number, or using the complement of one number? Does that seem relatively consistent with what we've been doing? Probabilities, relative frequency, they match well, as long as you think of the story along the lines of, if I pick one person's important from this sample, what's the probability of whatever it happens to be? Are we good? Let's have a look at that question that I avoided now. So hopefully it's ugly numbers, but it still counts. So we're going to look at probabilities, and they're breaking them into, do you think we used relative frequency to get this, or personal? If you ask someone, what's the chances? A personal probability is very subjective. But if I went and said to you, Eleanor, what do you think the chances that Dawn likes Pepsi? Eleanor might think, oh, I know Dawn quite well. I don't think she likes Pepsi at all, right? If you gave me a question like, what's the probability you think it's going to rain tomorrow? Since I've lived in Washington, I might say 0.9, right? Now, I'm not basing that on any fact. Aren't you just basing it on your gut feeling? And big numbers mean I'm pretty sure it's going to happen, and little numbers means it's not. So don't ask me, what's the probability I think a politician's going to lie on television tonight? Because my answer will probably be 1. Nah, let's be fair, 0.99999. How about that, right? Because there might be a fluky chance that one of them accidentally tells the truth. But when they do, it's mostly an accident, in my opinion. Okay,
I'm pretty sure 1 would be more accurate.
Probably. Right, now, according to Krantz, whoever that is, the probability that a random selected American will be injured by lightning is 1 out of 685,000. How do you think they got that information? Do you think they collected it as real data, or is it a gut feeling about what that person kind of thinks?
Definitely a gut feeling. Definitely.
You do? If Krantz was just a person, I'd agree to you. But when I look at it, it was actually looks like they have collected information. So how on earth could you do that? Well, I guess you know the population of America, and maybe you found out how many were struck by lightning. And couldn't you do it that way? Yes, Robert?
Oh, I said a retrospective study.
Oh, well, you've got choices. I'll leave it to you. Don't want to give all these away, because once you do the answer, you're just going to do it. Right, according to my neighbour, the probability that the tomato plant she planted last month will actually survive to produce fruit is a quarter. I think that's a personal one. Would you agree? It's just a gut feeling. According to the nursery where I'm purchasing my tomatoes, if you look after them, the probability that they'll produce tomatoes is 0.92. Isn't that more likely that it came from real data? Right. He sold thousands of these things and he knows roughly how many made it. The probability that a husband will outlast his wife for American couples is 3/10. You think that came from real data, right? From a relative frequency, right? Real data or just somebody, that's my feeling kind of thing. You think?
That one's gonna be real data.
Yeah. I mean, you can find things like, you know, when it's a couple, you can find out which one died first, right? It's not hard to find if it was male or female, typically. Although today, that combination isn't as binary as it used to be. I have a joke for you. Why do Scottish husbands die before their wives? Come on, say, I don't know. Why do Scottish husbands die before their wives?
I don't know.
Don't know.
Because they want to. No? I think Christy liked that joke, I don't know. Okay, Robert. At least he's not hissing and booing at me. Okay. Question 5, our big long story, but at the end of that story, you have to write down which one of these represents it. Let's pick just one, because again, I don't want to use all the good questions up. Question C then. Based on data from 1991 to 1993, the General Social Survey, the probability was about 0.367 in those years that a randomly selected adult who had never been married had divorced. That had ever been, okay, never been strange, right? So what's that? 36, almost 37% divorce rate, essentially. Wow. And how are we going to interpret this? Well, anybody, it's a lot of reading here, so if you can try reading, which one of them? I think I've got my answer. It's one of the top 4, it's not the last one. What's your gut feeling for how to interpret that? Any commitment?
I'm gonna say the third one.
Okay, let's read yours. Because I may change my mind after I read it, because mine wasn't the third one, but it doesn't mean that you're wrong yet. The relative frequency interpretation here applied here using a method which observes relative frequencies of outcomes over many repetitions. No, I'm not doing that one. And the reason I'm not doing that one is that one's better suited to throwing coins in the air, and you do it lots and lots of times and you write it down. And this is just different people who are married, right? So it's not the same as the same coin lots and lots of times. It's different people. So that's the only reason I kicked that one out. Okay, we've got 3 left. Maybe somebody can find what I picked.
I would go with number 1.
That's the one I chose. Let's see if I can go for why I chose one. It's a relative frequency interpretation that applied here using the method that makes an assumption about the physical words. Okay, well, that sentence is kind of bland. And it is used to define relative frequencies. Since we observed a large group of married people, right? And the relative frequency of the divorce amongst them, right? We didn't see every American that was married. You know that this survey is done out of, well, I can tell you how many people are in that survey. 1669 of them, right? But from that sample, 36.7% got divorced. I believe that's pretty accurate, isn't the divorce rate in America over 30% now?